In this video, we'll be talking about partitions of sets and the law of addition. So we'll start with the definition of a partition. A partition of a set A is a set of one or more non-empty subsets of A, such as A1, A2, A3, etc., such that every element of A is in exactly one set. So symbolically, we'll say A1 union A2 union A3 equals A. That takes care of every element of A is in 1. But also, if the subscript I is not equal to J, then A sub I intersected with A sub J is empty, and that takes care of every element of A is in exactly 1. So these are going to be disjoint subsets because they'll have empty intersection. So here's an example. The 4-element set A equal to A, B, C, D. Some partitions might be the set singleton A, singleton B, C and D. Or you might have A and B with C and D. Or you could have singleton A, singleton B, singleton C, singleton D. There are a number of others. In fact, it turns out there will be 15 different partitions of this 4-element set. And the key thing that we would have to check is that we get every element. So if you look, for example, at this first one, singleton A, singleton B, and then the doubleton C, D, you'll see that every element is present at least once, and every element is present only once. So these are disjoint subsets. So these are partitions. But we can also find partitions of sets that are not finite, like the set of integers. And some examples of a partition of the set of integers might be the set of all singleton n, such that n is an integer, or maybe the set of all integers such that they're less than 0, along with the set of all integers that are greater than 0, along with 0. And then we want to point out that if we had something like n in z such that n is greater than or equal to 0, with n in z such that n is less than or equal to 0, this would not be a partition, these two sets, because they don't have an empty intersection. The intersection is 0, so this would not count as a partition. Another way that we could fail to be a partition, let's look at this set. N is in the set of integers such that the absolute value of n is equal to k, and we let k run from -1 up. It's every integer from -1 up. So because one of these subsets would be empty, that is to say, if k is -1, then there is no integer whose absolute value is -1. This cannot be a partition. So the partition can't include empty subsets, and it can't include subsets which are non-disjoint. So we can think of partitioning a set as kind of a packaging problem. For example, how could one package a carton of, say, 24 cans of soda? Well, we could have 4 6-packs of soda, or 3 8-packs, or 2 12-packs, etc. But the key is that the sum of all of the packs must be all 24 cans, and each can be in only one pack. Now this brings us to the law of addition. If A is a finite set, and if we have a partition of A, such as you see here, A1, A2 up to AN, then the cardinality of A will be the sum of the cardinalities of these subsets. The basic law of addition can be rephrased as follows. If A is a finite set where A1 union A2 union ... union AN is equal to A, and where AI intersected AJ whenever I not equal to J is empty, then the cardinality of A is equal to the cardinality of A1 union A2 union ... union AN, and that's equal to just the cardinality of A1 plus the cardinality of A2 plus ... plus the cardinality of AN. So say we wanted to count the number of students in the class. We could just count them individually, one by one. That would be one way of counting the number of students in a class. Or we could group them. Maybe we could count the number of freshmen in the class, and then the number of sophomores, the number of juniors, the number of seniors, and then those who don't belong to any of these categories. So that would be one way of partitioning the class, because every student should either be a freshman or a sophomore or a junior or a senior or not belong to one of the categories, but they can't be in more than one category. However, we couldn't partition the class by major because some students have more than one major. There are double majors. So let's see an example here. The sophomore computer science majors were told that they must take one and only one of the following courses: cryptography, data structures, or JavaScript in a given semester. The numbers in each course, respectively, for sophomore computer science majors were 75, 60, and 55. How many sophomore computer science majors are there? Well, in this case, because we clearly have disjoint sets, meaning the students are taking one and only one of the courses, the law of addition can be applied. So there must be exactly 75 plus 60 plus 55, which is 190 computer science majors. On the other hand, if it was determined that all junior computer science majors should take at least one of the courses algorithms, logic design, and compiler construction, and we were told that the number in each course was 75, 60, and 55 respectively, we wouldn't be able to use the law of addition right away. But after further investigation, if we knew that 10 juniors took all three courses, 25 took algorithms with logic design, 12 took algorithms with compiler construction, and 15 took logic design with compiler construction, then we could determine the number of computer science majors. So we can break these into sets. Let's A be first, all the computer science majors. Then the subsets will be the set of all juniors who took algorithms, the set of all juniors who took logic design, the set of all juniors who took compiler construction. So we know that the cardinality of A, we want to add up the cardinalities of these subsets, but then we need to subtract the number of students who are enrolled in 2 or 3 courses because they get counted more than once. So a Venn diagram can be a helpful way to visualize this problem. And we have that picture here. And here they've labeled each section of the Venn diagram with a different number. So these numbers are just breaking it into parts and giving them labels. So we'll see that the entire universe is naturally partitioned into these subsets labeled 1 through 8. And that the set A is partitioned into the subsets labeled 1 through 7. So 1 through 7, they make up A, whereas number 8 is students who are in the universe but who are outside of A. In other words, students who are not junior computer science majors. Note that students in the subsets labeled 2, 3, and 4 are double counted, and those in the subset labeled 1 are triple counted. So let's take a look here. Students in the subsets 2, 3, and 4 are double counted because they get counted as students taking algorithms, and then they get counted as students taking compiler constructions or logic design. And then the students here get counted 3 times because they're taking all 3. So how do we address this problem? To make the adjustment, we'll subtract the numbers in regions 2, 3, and 4. But then we'll have removed those in region 1, so we'll add them back in, and I'll show you what we mean. So the cardinality of the set A should be the cardinality of the union of the 3, which should be the cardinality of A1 plus the cardinality of A2 plus the cardinality of A3, subtract all of the duplicates, and then add in the triplicates because they got subtracted one too many times. And this is going to end up looking like the cardinality of A1 plus the cardinality of A2 plus the cardinality of A3. Then we'll subtract the intersection of A1 with A2, subtract the intersection of A1 with A3, subtract the intersection of A2 with A3, but then add in the intersection of all three. So with the information that we were given above, this was 75 students who took the first course, algorithms, 60 students who took logic design, 55 who took compiler construction, and then we're subtracting the intersections. So 25 of the students who took algorithms also took logic design, 12 of the students who took algorithms also took compiler construction, 15 of the students who took logic design took compiler construction, and then 10 students took all three. So we add these, then we subtract these, then we add this, for a total of 148 junior computer science majors. What we were just using has a name, and it's called the law of inclusion-exclusion. So if we have finite sets, then the law is going to be that the union of two finite sets will be the sum of the cardinality of that union is going to be the sum of the cardinalities of the individual sets minus the cardinality of their intersection. Whereas if we have three sets, like we did in the previous example, the cardinality of the union of the three sets is going to be, first we add the cardinality of each set individually, then we subtract the cardinality of the intersections, there'll be three of those for three sets, and then we add the cardinality of the triple intersection. This law will extend to more than three sets, as will be explored in these exercises that we're about to do. So in this section, we've seen that being able to partition a set into disjoint subsets gives us a nice and easy way to count the elements. So here are some examples. Which of the following collections of subsets of the plane, so just our typical XY Cartesian plane, and we'll denote that by r squared, which of the following collections of subsets are partitions? So we'll remind ourselves that in order to be a partition, we need every element in the plane to belong to at least one set, and we need every element in the plane to belong to at most one set. In other words, exactly one set. So let's think about the first set that we're given here. This is the set of sets of ordered pairs x and y. Remember, these are subsets of the plane, so they're ordered pairs, sets of ordered pairs, such that x plus y is equal to c, and we're going to run that collection over every real number c. So some examples would be the set of ordered pairs x comma y such that x plus y equals 1. That's a set in this collection. Or the set of ordered pairs x comma y such that x plus y equals the square root of 2. That's also a set in this collection because 1 is a real number. Square root of 2 is a real number. And there are many, many, many uncountably infinitely many more sets in this collection. But that gives us an idea of what this collection might look like. And what geometric object are we describing when we say x plus y equals 1? Well, we know that it's a subset of the plane. And x plus y should give us, x plus y equals 1 should give us the line of slope -1 with y-intercept 1. So this is the set of ordered pairs, x comma y, such that x plus y equals 1, if I drew it visually. The next set would be the line which intersects the y-axis at square root of 2, and so on. So if we ran this collection over every possible real number, we would get the set of all lines of slope -1. So this is the set of all lines of slope -1. And if we think about this being a partition, and we ask ourselves, can every point in the plane lie on a line of slope -1? Well, absolutely. Just imagine filling in all of the gaps with more and more and more lines of parallel slope. And then the other question we have to ask is, can any single point lie on more than one of these lines? And the answer is no, because the lines are parallel. They will never intersect each other. So this is indeed a partition. It's a partition because if I take the union of all of these sets, which I'm representing as parallel lines, then I will get the entire plane. I will be able to cover it with these parallel lines. But also, these lines will never intersect each other, so each point in the plane can belong to at most one of these lines, exactly one of these lines. So it is a partition. Now let's think about the set of all circles in R2. So again, we know it's a subset of the plane. The question is, can I partition the plane into circles? And of course, I'm drawing terrible circles, but for the same reason as the lines, if we think about drawing more and more and more circles, and all of them are centered at the origin. Oh no, in this case, they're not all centered at the origin. So I could draw a circle like this. Well, then you can see I've got a problem because I've got two circles intersecting. So this is not a partition because these are not disjoint sets. Now let's think about the set described in part C, the set of all circles in R2 centered at the origin. So that seems like it's likely to be a partition because I could fill in all of these gaps with circles, so every point in the plane would lie on some circle. The only problem that I might have is the origin itself, because there is no circle of radius 0, but that's why they've thrown in the set 0, 0. So they threw in the origin, so C will be a partition, because every point in the plane will lie on at least one circle, and every point in the plane will lie on at most one circle. There's no way for these circles that are centered at the origin to intersect each other. They're just going to be nested within each other. So that's a good partition. And then lastly, the set of all ordered pairs x and y such that the ordered pair is in the plane. So this set is R2 itself, and R2 is a valid partition of itself. Again, if we think about what's required to be a partition, R2 does cover all of R2, and since there's only one set in the partition, we don't have to worry about disjointness. So it's sort of a trivial partition of itself. The whole set is a partition of itself. Okay, next example. Show that the sets here form a partition of Z. Describe the partition using only words. So the sets are the set of all 2 times n such that n is an integer. So let's think about what that set might be. We can play around with some easy integers, like 0 is an integer, 2 times 0 is 0, or 1 is an integer, 2 times 1 is 2, or 2 is an integer, 2 times 2 is 4. What about negative 1? 2 times negative 1 is negative 2, or negative 2, 2 times negative 2 is negative 4. And the picture that I'm starting to see is that this appears to be the set of all even integers. Now let's look at the other set, which is the set 2n plus 1 such that n is an integer, and let's try the same thing. Let's plug in some easy integers. So if I plug in 0, I get 2 times 0 plus 1, that's 1. If I plug in 1, I get 2 times 1 plus 1 is 3. If I plug in 2, I get 2 times 2 plus 1, that's 4 plus 1 is 5. Or I could plug in negative 1, so I get 2 times negative 1, which is negative 2, plus 1 is negative 1. If I plug in negative 2, I get negative 4 plus 1, that's negative 3. And so this appears to be the set of odd integers. So we wanted to show that this is a partition of Z. Well, we know that every integer is either even or odd, but not both even and odd. So partitioning the set of integers into the even integers and the odd integers is a perfectly valid way to partition the set. So now let's look at some inclusion and exclusion type of problems. Part A says a group of 30 students were surveyed, and it was found that 18 of them took calculus and 12 took physics. If all students took at least one course, how many took both calculus and physics? Illustrate using a Venn diagram. So let's start by remembering that I'm going to let C be the set of all calculus students, and then I'm going to let P be the set of physics students, and we'll start by remembering the rule that the union, the cardinality of the union, should be equal to the cardinality of C plus the cardinality of P minus the cardinality of their intersection. And what we know is that 18 of them took calculus, so this is 18, and 12 of them took physics, so this is 12. So the union, which was 30, because there were 30 students in the survey, or at most 30, is equal to 18 plus 12 minus the cardinality of the intersection, but 18 plus 12 is already 30. So we know that the cardinality of the intersection should be 0. So if I wanted to draw a Venn diagram, I would want to make sure that my two bubbles, one for calculus and one for physics, don't intersect at all, because the intersection is 0. Then in part B it says, what is the answer to the question if 5 students did not take either of the 2 courses? So if we go back up and look, we knew that all students took at least one course, and that's how we knew that the union would be 30. So if 5 students did not take either of the 2, then our union should be all of the students surveyed minus 5, so 25. And then we have 25 is equal to 18 plus 12 minus the intersection. So 25 is equal to 30 minus the intersection. So I can subtract 30 from both sides, and I get minus 5 is the negative of the cardinality of the intersection, so the cardinality of the intersection is 5. So now if I wanted to draw a Venn diagram, it should look a little different. I do have an intersection, so these 2 sets will overlap. I have calculus, I have physics, I have an overlap. I also have students that didn't take calculus or physics, so I have some area outside of these bubbles. Okay, here's another example of that type. A survey of 300 people found that 60 owned an iPhone. So I'm going to say, let's let capital I be iPhone owners. Then 75 own a BlackBerry. And 30 own an Android. So I'm going to let capital B be BlackBerry owners and capital A be Android owners. So the cardinality of I is 75. That's given in the problem. The cardinality of, 60. And the cardinality of B is 75. And then the cardinality of A is 30. Furthermore, we know that 40 owned an iPhone and a BlackBerry. So I'm going to say that's iPhone intersected BlackBerry. It's 40. And 12 owned an iPhone and an Android phone. So I intersected A will be 12. And 8 own a BlackBerry and an Android phone. So B intersected A is 8. And finally, we have 3 own all 3 phones. So that's I intersected with B intersected with A. The cardinality is 3. So that's just the information given in the problem. The first question that it asks is, how many people surveyed owned none of the 3 phones? So owning none of the 3 phones, that should be the surveyed minus cardinality of I union A union B. And we know that our rule says that that's 300 surveyed minus, first we're going to have cardinality of I, cardinality of B, cardinality of A. I'm going to put parentheses here, so I'm going to start by saying this is plus, then minus the cardinality of the intersections, and then plus the cardinality of the triple intersection. but I have to remember to distribute that minus all the way across. So that's going to be 300 minus 60 minus 75 minus 30. Minus times minus gives me plus, so plus 40 plus 12 plus 8, and then minus times plus gives me minus, so minus 3. So it looks like this is 300 minus 165 plus 60 minus 3, which is 300 minus 108. So 192 of the people surveyed owned none of the 3 phones. Then it asks how many people owned a BlackBerry but not an iPhone. So that should be the number of people who owned a BlackBerry minus the number of people who owned BlackBerry and iPhone. So that's 75 minus 40, or 35. And finally, how many owned a BlackBerry but not an Android? That should be the number of people who owned a BlackBerry minus the number of people who owned a BlackBerry and an Android, or the intersection of B and A. So that's 75 minus 8, 67. In the next exercise, we'll use the 2-set inclusion-exclusion law to derive the 3-set inclusion-exclusion law. So we have the laws in the lecture above, but let's go ahead and see if we can use the 2-set inclusion-exclusion law. So I'm going to write that here, and let's see if we can use it to derive the 3-set inclusion-exclusion law. So the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection. That's the 2-set inclusion-exclusion law. Now suppose I have 3 sets. Maybe I have A, B, and C. So I'm going to let me give them different names. So I have 3 sets there, P, Q, and R. And I'm going to let A equal P, and I'm going to let B equal Q union R, and then I'm going to plug it into the formula that I already have. So that tells me that P union Q union R, if I think of this as A union B, then that should be equal to the cardinality of P plus the cardinality of Q union R minus the cardinality of Q, let's say, of P intersected with Q union R. And over here on the left-hand side, we know that P union, and then in parentheses Q union R, is the same as just P union Q union R, so we don't really need those parentheses. Then here I have cardinality of P. I'm not going to change anything there, but for the cardinality of Q union R, I'm going to refer back to this rule and replace it accordingly. So it looks like that should be the cardinality of Q plus the cardinality of R minus the cardinality of Q intersected with R. So that is just this much. These correspond. And then here, this set, P intersected with Q union R, I can write this as P intersected with Q union P intersected with R. So I've just distributed the intersection over the union. So this is going to be cardinality of P plus cardinality of Q plus cardinality of R minus cardinality of Q intersection R. That all stays the same. Now I want to apply my inclusion-exclusion law for two sets again here to this set. So I'm thinking of P intersection Q as being like my A and P intersection R as being like my B. Then that's going to be, I'm going to start a parenthesis. It's going to be cardinality of P intersection Q plus cardinality of P intersection R minus the cardinality of P intersected with Q intersected with P intersected with R. Close off my parenthesis there. So again, this first part is not going to change. I still have cardinality of P plus cardinality of Q plus cardinality of R minus the cardinality of Q intersected with R. Now I can start distributing this minus across. So that's going to be minus the cardinality of P intersecting Q minus the cardinality of P intersected with R plus the cardinality of P intersected with Q intersected with P intersected with R. I just went ahead and dropped those parentheses. But now I'll notice that I'm intersecting with P twice. And I don't need to write that twice. So I can write it only once. And then I'll see that it's exactly the law that we had in the lecture for three sets. First, I add the cardinalities of each of the sets. Then I'll subtract the intersections, the cardinalities of the intersections. And there are three intersections. Q intersected with R, P intersected with Q, P intersected with R. And then finally, I want to add the intersection of all three of them. So you can see that through successive applications of the inclusion-exclusion law for two sets, we were able to derive the inclusion-exclusion law for three sets. Then the question asks us to state the inclusion-exclusion law for four sets. So we're just going to follow this same pattern. We're going to say, well, now I have maybe P, Q, R, and S. And I want to find the cardinality of the union of all four of them. Then I know that I'm going to need to add their cardinalities. P plus Q plus cardinality of R plus the cardinality of S. Then I want to subtract the cardinalities of their intersections. So that should be minus the cardinality of P intersected with Q, minus the cardinality of P intersected with R, minus the cardinality of P intersected with S, minus the cardinality of Q intersected with R, minus the cardinality of Q intersected with S, minus the cardinality of R intersected with S. Then I'll add in the cardinality of the triple intersections. So that will be plus the cardinality of P intersect Q intersect R, plus the cardinality of P intersect Q intersect S, plus the cardinality of P intersect R intersect S, and plus the cardinality of Q intersect R intersect S. And then finally, I'll subtract the intersection, the cardinality of the intersection of all four of them. P intersect Q, intersect R, intersect S. So you can see a pattern here, which is that I'm alternating between adding and subtracting the intersections of various sizes. So first I just add in the cardinality of the sets themselves, then I subtract the double intersection, or the intersections of two sets, then I add the intersections of three sets, and then I subtract the intersections of 4 sets. So it's a little bit of alternation there, and that pattern is going to continue if we wanted to do this for 5 sets and 6 sets and so on. Okay, the last question is just a little more counting here. To complete your spring schedule, you must add calculus and physics. At 9:30, there are 3 calculus sections and 2 physics sections, while at 11:30, there are 2 calculus sections and 3 physics sections. How many ways can you complete your schedule if your only open periods are 9:30 and 11:30? So let's write this down. At 9:30, there are 3 possible sections of calculus and 2 possible sections of physics. And at 11:30, you have 2 possible sections of calculus and 3 possible sections of physics. How many different ways can we complete our schedule? Well, here we're going to apply the multiplication rule that we learned in the previous lecture. First of all, at 9:30 I could take calculus. So let's say I choose calculus at 9:30. Well, I have to have calculus and physics, so that means at 11:30 I'm taking physics. And how many ways are there to make this schedule? There should be 3 times 3 ways. First, I choose my calculus course, and for each calculus course, I have 3 choices of a physics course. So this is multiplication rule. 3 times 3 is 9, and that's for the 9:30, choosing calculus at 9:30. Or I could say, no, I want to take physics at 9:30. That means I must take calculus at 11:30. So I have choice of 2 physics classes and the choice of 2 calculus classes, so 4 schedules. And then I will add them up. We'll say there are a total of 9 plus 4, which is 13 possible schedules. That should be the final exercise in this lecture. So we'll leave it here for now, and then in the next video, we'll learn more about permutations and combinations.